now. Welcome to lecture 6 of our series. Today I'm going to be going into the maximal functions, which are a very, very excellent topic in harmonic analysis. They're sort of the bread and butter, or one of the bread and butters of the field. And in particular, there are a couple other ones like singular integrals and square functions. But this is going to be the ones that we're going to focus on because it's going to tie into the spherical maximal function and its discrete version, which form the second part of our course. Okay, so this is the Euclidean versions of those, but sort of the ones that arose first and the ones that we understand best. So in this lecture, we're going to talk mostly about the Hardy LIttlewood maximal function. And probably towards the end or in the next lecture, we'll get to applications and then the spherical maximal function. All right. The Hardy LIttlewood maximal function is one of these pillars of harmonic analysis. So how is it defined? Start with a nice function, say continuous, compactly supported on Euclidean space, Rd. And it just takes real values. Now for each point x inside of your Euclidean space, you can look at a whole bunch of averages around that point. And these averages are going to be defined by each ball centered at that point. Okay. In particular, you look at this integral expression, where I have this is Lebesgue measure. So I take my nice function, maybe it looks like a graph. I pick my favorite point x, and I pick my favorite width, say 1. Right, so I have a ball of radius 1 about x. And I average the value of the function in that interval. That's the one-dimensional version of this. And of course, in higher dimensions, I take an actual, I have a point space, average over the whole ball centered at x. This is the entire ball, like all of the points inside the open ball. So it is a d-dimensional subset of Rd. It's very thick in particular. And this integral makes sense without naively. And honestly, if I wanted to do convolution, then I should have said x minus y. So I have all of these averages at each point, one for each radius of the ball. And you form the maximal function, or the Hardy LIttlewood maximal function, which might also be well considered as a Hardy LIttlewood Wiener maximal function, by taking the supremum amongst all these averages, with the twist that I take the absolute value of the average. Great. This seems like some sort of strange function, some strange process to do to my original function. And indeed it is, but it turns out that it doesn't, in many quantitative ways, it doesn't destroy the original function too much. You can get a lot of precise properties about the original function are reflected in the maximal function. Okay. So our main theorem for today is Hardy LIttlewood Wiener theorem, which says that M is a bounded operator, right? It's an operator because I started with a function and I sped out another function through this process of looking at all averages and taking the biggest one. This is a bounded operator on LP spaces for p greater than 1, and it's weak type 1, 1. And this is sharp in the range. And this weak type 1, 1 inequality is exactly this expression right here. Remember that less sim means less than or equal to a constant times whatever is there. This constant is allowed to depend on the dimension for us, but it doesn't depend on that function that we plug in. All we assume is that that function has a finite L1 norm. So it's good to recall what the LP norms are. So remember that the LP norm of a function f on Rd is simply the integral of the absolute value of f to the pth power with respect to the Lebesgue measure on all of Rd and to the 1 over p exponent. These LP spaces have a lot of nice properties, right? They're complete for one. They're also closed under addition and scaling. So they're linear spaces, right? Scaling is easy to see. If I took the absolute, if I took the LP norm of a constant c times f and LP of Rd, well, that means I put it in a c here, right? That gives me an absolute value of c to the p, which then comes out as a absolute value to the 1 over p. So altogether, it's just absolute value of c times f in LP of Rd. And Minkowski's inequality, or the Holder's inequality, implies that if I have two functions in LP, and I look at their sum, we have the triangle inequality. The LP norm of f plus g is at most the LP norm of f plus the LP norm of g. And now I've started using some shorter notation here, where I've left off the space I'm considering, and I'll just write it as LP if it's clear from context, or even leave off the L if it's clear from context as well, right? And this is actually for, so this works for all p greater than 0, but this is only true for p greater than or equal to 1. One thing I didn't say is we're going to want to consider p equals infinity. So that's for, this is a great expression for that. But there's also L infinity. Of Rd, and this is the essential supremum of the absolute value of your function. What's that? That is the smallest constant, say k, such that f is less than or equal to k almost everywhere with respect to Lebesgue measure. Right. So in particular, f could just be a constant function on Rd. If it's a constant 1, every point it spits out 1, then the L infinity norm is exactly 1. Okay. This also satisfies the triangle inequality. So this works up to p equals infinity. And of course, it satisfies the scaling property as well. So what it means for M to be a bounded operator now on LP means there exists some constant. It means for each p, that's greater than 1, there exists some constant, positive, call it C. And it is allowed to depend on P, and it is allowed to depend on Rd, on the dimension, such that the LP norm of this maximal function is at most that constant times the LP norm of the original function. And then weak type 1,1 again was just this other expression here. And this other expression, to break it down, this is a super level set. This expression right here, I'm looking at all the points where the maximal function is greater than some altitude alpha. I should say for all positive alpha. So you look at the super level set and you take its Euclidean, sorry, its Lebesgue measure in Rd. That is a bounded function bounded by the inverse of alpha times the L1 norm of f. A priori, it's not even clear that why isn't it all of Rd or something, right? Which would have infinite mass. but it turns out it has finite mass for each alpha, and you can quantify exactly how much. So that's an important part of this theorem. Before we get into a bit about why anyone would ever try something as crazy as just consider all the averages, take the biggest one, then start bounding it by the original function, let's maybe orient ourselves with what each of the averages is, what it's doing. Great. So each average is an average in the sense that it doesn't increase the size of the function. Now, it might do so at an individual point or a whole bunch of points, but it doesn't do so in this LP sense. Okay. In particular, if you consider the measures where I take the indicator function of the ball of radius r, this is centered at the origin, so b of r equals ball of radius r centered at 0 in Rd, and 1 of x for any measurable set x, or really any set, is just going to be 1 at a point, let's say y. 1 if y is in x, my set, and 0 otherwise. You can't see that. So this is a function right here, 1 of b of r. It's just 1 on the ball, 0 outside of the ball. But my measure is going to be a probability measure, so I'm going to normalize by the volume of that ball. Right? This, by probability measure, I just mean that the integral of mu of r over all of Rd is equal to 1. Now, since we have that, this is true for every r, every positive r. Since we have that, Young's inequality, which says f convolved with g in LP is at most g in L1 times f in LP, it tells us that the LP norm of any fixed average applied to my function is at most the LP norm of the original function. Okay. So going back to my picture, or our picture, you can see if I picked this to be a local minimum, and I look at the average in some big interval, let's take our interval now to be, say, maybe here, up to here, so we see there's some really big valleys. This average is going to be bigger than that point, than the value of the function at that point. So my average can actually honestly increase the function at various points. Of course, at this local maximum, though, any small interval around it, let's say is going to have a lower average, smaller than it. So it can also decrease it. But our maximal function is always going to take the biggest average, which, as you shrink that interval around a local maximum, is really just going to be the value of that point again, if your function is, say, continuous, continuous and differentiable, because of the mean value theorem. Sorry, I meant continuously differentiable by the mean value theorem. Oops. Great. So these averages can actually change the size of the function pointwise, but overall, in the entirety of the whole space, when I measure the size of my function in terms of an LP norm, it doesn't increase it. This bound is sharp. You can't have a strict inequality. For instance, I can't have that a of r f is less than 1/2 of f in LP for all f. It can happen for some f, but not for all f, by just taking the function that is 1 in a big box and expanding it. So if I take a really big box, a box that is far bigger than my average, when I take this little ball and I look at it around that box, it's going to be, it's not going to change the function. So I mean, take f to be 1, the indicator function of a gigantic box. Then f, so the average of AR of f, when r is much smaller than the size of that box, is basically f. I didn't change f too much because the edges are so small in comparison to the inside. And if you let that box expand, you see that this constant of 1 here is the best possible. Okay. Now, we know this is true for each r. So if I take the supremum over all r of the LP norms of the averages, it's always at most the original function, the LP norm of the original function. And this is true. This was true for all p between 1 and infinity. But the maximal function isn't taking the LP norm and then the supremum. It's doing the opposite. It's taking the supremum before the LP norm. Minkowski's inequality tells us that this one, where I take the supremum before taking the LP norm, is bigger than taking the LP norm and then the supremum. More generally, Minkowski's inequality says that the integral of, say, a function in x and y to the p dy and then to the q over p dx, all to the 1 over q. Sorry, so if I have a function of 2 variables and I take the LP norm followed by the LP norm in one variable and the LQ norm in another variable, then this is at most the LP norm in switching the order of p over q. Oh, that's dy, 1 over p. When, wait, so the bigger exponent goes on the outside. So when p is greater than or equal to q. And in here, this is an L infinity instead of a p. And that same Minkowski's inequality holds. If I take an LP norm of, I have a function of 2 variables, I take its LP norm for a finite p, say 2, it's L2 norm in one of the variables, and then its L infinity norm, that's smaller than taking the L infinity norm in the other variable, and then the L2 norm in the first variable. So Minkowski, sorry, not Minkowski, the Hardy LIttlewood Wiener theorem is really saying that we get a weak version of this theorem when you move the sup inside. The weak part comes in, there's some constant here that we haven't made explicit yet, but you still get the LP boundedness. And it's weaker also because this is, this bound isn't true right? This bound is not true when p is equal to 1, whereas this bound is true for all p greater than or equal to 1. Great. So let's see why it fails when it's p equals 1. Okay. Great. I'm going to just take I'm going to fix an honest function and I'll compute with it. Oh, one important point. For those who aren't familiar with LP functions, or haven't worked with them in a while, this is the LP space. I gave you the LP norm. The space of LP is an equivalence class. So each element of an LP space is an equivalence class of functions. Those functions are the same almost everywhere, meaning up to a set of measure 0. And they have the same LP norm in that equivalence class. So I'm taking now an L1 function, and my L1 function is just going to be the characteristic function of the interval -1/2 to 1/2. So I'm going to pick one dimension. I have the characteristic function of a -1/2 to 1/2. This is 1, height 1. This is -1/2. This is 1/2. So it's 1 inside here and it's 0 outside. This again is just a representative function in L1. There are a whole bunch of equally valid representations. For instance, at the point 2, I could make it be a bajillion, but then 0 everywhere that isn't -1/2 to 1/2. Or in any countable set, I can just make it be whatever value I want, and that doesn't affect the L1 norm. But we'll just pick, in all of the things we go forward, we're going to pick our functions to be almost continuous on the whole real line. There'll be at least simple functions like this. They're built out of indicator functions of intervals, or they're a Schwartz function where they have continuous compact support, or some other nice property where they're an honest function. But all of these bounds that we talk about are really only going to care about the L1 or LP norms, and therefore apply to any other instantiation of that function as an LP function and in the same equivalence class. Great. Okay, so that technicality aside, we can calculate the maximal function around this point, or of this function, sorry. How do we do that? Let's start by zooming in. Okay, I have -1/2 to 1/2. It's 1. It's 0 outside of this. If I take some point inside and I look at all the intervals that are symmetric around that point, but contained inside -1/2 to 1/2. The average over this interval is 1, because every value inside that interval is just 1. And again, it's a probability measure. So it's normalized to counteract the width. Okay, so all of those averages are at least 1 for every point inside this interval. Even if I get really, really close to the edge, I can still find some smaller interval that contains that point. And this still applies. I can find some average that gives me at least 1. So we obtain the first bound in the interval. I should maybe actually write this as open. We get this lower bound. Okay, if x is inside -1/2 to 1/2, then the maximal function is at least 1 there, and therefore this term is true. Now it leaves the question of what happens outside of that interval. Again, open. And my claim here is that it decays like 1/x roughly. Cool, cool. How is that? How do we see that? Let's say I've taken some point over here, pretty far, far away. Well, if I look at nearby averages of it at this time, well, it's 0 on all of those averages, so it hasn't really picked up anything. But a lower bound of 0 for a function that's non-negative is a very terrible bound. Let's take a bigger average. we take an average now that contains this a big chunk of our support of the support of our function. Okay. In that case, I pick up all of this mass right here. And okay, it's still 0 all over here, but if I pick things correctly, then I'll actually take this interval to be the one that goes all the way to -1/2. And then so if this is x, this goes to something else, I think 2x minus 1. And I pick up all of the mass inside of here. That has mass 1 because it's an interval of height 1. So it's an interval of length 1 and has height 1. So it's just 1. And the length of this, again, this radius is x plus 1/2 because that's minus -1/2. So this also has x plus 1/2, which combined to give 2x plus 1 when x is positive because I've drawn it on the right. But similarly, just by reflection, you get the same when x is less than 0, when x is negative. And that is how you get this second term. It says that whenever x is not inside that support, you get this bound. And now it's just, it's a straightforward computation, right? We're going to say that, oops, if I have m of 1 minus 1/2 to 1/2 of x is greater than or equal to, what was it, 1 of minus 1/2 to 1/2 plus 1 of everything outside of that, oops, open intervals, to x plus 1. Well, we try and integrate this in L1. Okay, well, the absolute value is superfluous. We've seen that this is a non-negative function. I'll remove that. But now I'm integrating this side. Okay, that's just 1 right here. But this is plus something that is basically like the integral from 1 to infinity of 1 over x. I don't need the absolute values. Dx. And that we all know to be a divergent integral. So this right-hand side is actually equal to infinity. So that means that the L infinity norm, sorry, the L1 norm of this maximal function is infinite. It's an L1 of R1. But the L1 norm of our function oops, that's an R1. Was just 1. Okay. Now you might be concerned that, oh, well, what if I take a different pth power? Well, if I take the pth power, then I know that this is true. And if our theorem is supposed to hold, this better be a finite thing. This expression better be a finite number, because we've assumed that, we assume that our function LP is going to be finite, which it is when f is the indicator function of the unit interval. It's actually just 1 again, the LP norm. And what we find is that, okay, this, because the supports are disjoint, this actually becomes well, this just becomes the following expression. I can take the p norms of the two different functions because they're disjoint support. Again, this is norm 1. And now this is actually a function like the integral from 1 to infinity of x to the p, which we know has a finite integral, which is great. Okay, so that's not a counterexample when p is greater than 1, but it is a counter. It is show that the theorem is sharp when p is equal to 1. What we saw is that we started with a compact function and a compactly supported function, and we calculated the maximal function of it. So what we saw was when all of our mass is concentrated in a neighborhood, in a compact set, when you look far away, you have decay that looks like 1 over x in R1 times the size of that set, which we just assumed to be finite. And now that actually works as soon as you have a function that is not 0 everywhere. You just take some region of it that is positive, or completely negative, and you just take it to be bounded away from 0, and you can do exactly the same argument. The constant changes, but the decay rate as you move away from that support is only like 1 over x. And that is a function that never lies in L1. It's a function that always lies in LP, but it never lies in L1. So we've actually deduced that the integral is finite for any on any LP space. The maximal function in LP is finite for any p greater than 1 if your function is compactly supported. But the Hardy LIttlewood theorem says that when you could divide that by the LP norm of the original function, that constant doesn't depend on the function at all. Okay, that's an important thing that we'll have to take care of. There's a little bit of a gap, right? So I think in the comments, maybe Rob just said that as well. That this gives you.
Sorry about that. I didn't realize you were going to say it.
No, that's great. Yeah. So you actually see that any non-trivial function, its maximal function, any non-trivial function in L1, its maximal function is not in L1. But we saw it can give you an honest function. It gives you something that you can appreciate and understand, but it's just this way of measuring the size of a function is infinite. Okay. However, it does actually, one of the claims of the Hardy LIttlewood Maxwell theorem is that we do have the weak type bound at p equals 1. The weak type bound at p equals 1, which just to remind you, said that when we look at the Lebesgue measure of the set of points where the Maxwell function is greater than some altitude alpha, which is positive, this is at most some constant, depending on the dimension, alpha inverse, f in L1. This decay rate of 1 over x are exactly the kind of functions that satisfy this type of bound. And this is why you might suspect that such a thing holds true. One point is also if we know it's never true, but suppose you knew that your maximal function was in L1, so that you knew something like m f in L1 was less than or equal to, say, the same constant CD of f in L1. Well, that would imply this statement by the Chebyshev-Markov inequality. And so this, while we know that this is false, patently false, just basically horrifically untrue, because every non-trivial function has infinity on this side, we do know that this weaker statement, implied by what we would hope to be true, is valid. And so it's a nice surrogate. Great. Are there any questions up until this point? I'll power through. Okay, so the contraction inequality we had is just saying that each average maps LP to LP, but with a norm of at most 1, suggests to you that the maximal function, which is the supremum wedged inside of the LP norm, can't really map, it can't map functions that are really different from each other qualitatively to functions with a very different qualitative type. So what do I mean by that? I mean, if I start with a function that is very broad and shallow, oops. It's not fluctuating too much. Let's make it fluctuate even less. Then the maximal function, well, each average, which says it maps this is a very good example of a function in all infinity. It's always bounded by, say, 10. Well, the average of this thing is always bounded by 10 as well. And sorry, each average, one moment. Excuse me. Yeah, so each average, it takes an L infinity, a bounded function, to another bounded function. It cannot, if this is satisfied, it can't do something like when I play the averaging operator, it can't be like, shoop, 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 shoop. It can't do any sort of spikes that really go above it from before. Similarly, if I started with a function like this, that had a lot of tall, spiky behavior, this could be an L1. Remember, 1 over x to the p is an L1 when at least for big X. And this says that this contraction inequality again says that, okay, I'm going to map myself to another tall, spiky function, but it's not going to suddenly make it broad and shallow. Right? It's not going to convert anything that's red to something that looks black or vice versa. And dimensional analysis actually makes this argument rigorous. So this is again, for people who haven't seen LP spaces a lot or haven't worked with them in a while, sort of if P is very big, you can think about your LP functions as being broad, shallow functions. They can have a very wide range of support, but they can't suddenly go to infinity or if they get really large at around some point, then that's going to force the LP norm to be very large because of that. And a prototypical LP space is L infinity here, right? If you're bounded by a constant almost everywhere, then you can't have a tall spike that goes beyond that point, beyond that height of your function. And similarly, L1 functions, because of this sort of 1 over x to the p behavior, you can integrate them. They can be quite narrow and spiky, but if I take a very broad, shallow function, say it's 1 on some huge interval, then that has an enormous L1 norm. For instance, if I take a constant function, the constant's always 1 again, that's a perfectly fine L infinity function, but that is not an L1 function because it's 1 on an infinite volume, so the integral's infinite as well. Great. That's sort of an aside. But you can use dimensional analysis to show that this maximal function doesn't have any other mapping properties. Okay, it doesn't map LP to LQ when P and Q are not the same. Dimensional analysis is just you pick some nice function, like before we picked the characteristic function of the interval minus a half to a half, and then you consider all dilates of that function. Right? And so I will rescale my function so that, say, it's supported between minus delta over 2 and delta over 2. But I'm going to keep the LP norm preserved, so I'll scale it by an appropriate power of delta. And then when you do, you can get the same lower bound for the maximal function that you had before, and you can just compare LP and LQ norms. And you can show that the ratio would have to go to infinity if you consider this family of functions where the family is defined for all delta greater than 0. All right, let's get into some more properties of the Hardy LIttlewood maximal function. Each average has a lot of smoothing to it. Okay, we saw that it's a contraction in LP, meaning the LP norm of f, of the average of f, is at most the LP norm of f, but you can also smooth out your function. So a very classical example of this is, suppose I started with a continuous function just in one variable on R, and I look at any fixed average AR of f. Well, that is now a continuously differentiable function, right? I started out with something continuous. I applied this average everywhere to it, and I gained a derivative. That's pretty cool. Very useful. A lot of calculus relies on that, essentially. And you know exactly what its derivative looks like in this case as well. So this is a good exercise from calculus just to remind yourself. And so you might think, well, all right, each of my averages smooths out my function. But then I do this, again, as far as we can consider, bizarre behavior of taking the biggest average, taking the absolute value and the biggest average. First off, absolute value already destroys some regularity of a function. If you just think of the function f of x equals x, and then you compare that with the absolute value of x, right? You have this, and then you have that kink at 0. That is continuous, but not differentiable anymore. You went from something that was C infinity now to something that is only continuous. Okay, despite that, you can show that this maximal function is lower semi-continuous, meaning that these super level sets, the set of points where the maximal function is bigger than some altitude, is actually an open set inside of RD. It's not something, it's not some fractal or anything crazy. It's an honest open set, which is good. Unfortunately, something like this for the maximal function doesn't hold. It's harder to get a grasp of what the derivative of the maximal function would be. But there has been some recent work in that in the past 25 years or so. Okay, let's actually get to the proof of Hardy LIttlewood's theorem. Maybe starting with some, we'll probably in this lecture just handle the first 2 steps. So we'll do some standard reductions to get down to proving a weak L1 inequality, or a weak type 1-1 inequality, as it's also known, for sufficiently nice functions, and that's good enough for all L1 functions. Then in the next lecture, we'll probably go on to interpolation. That tells you how to use this weak 1-1 inequality and the L infinity inequality to get all the LP inequalities in between. Cool. What are the standard reductions? Well, so this is where your graduate course in real analysis comes in quite handy. You have to recall all these things like the dominated convergence theorem, monotone convergence. There's another, Fatu's lemma as well. So it turns out for us that monotone convergence and dominated convergence are how people mostly describe these reductions. All right, first stop. I mentioned before that any LP, any function, I mentioned the LP spaces are complete. I did mention that continuous compactly supported functions are dense inside each LP space for finite P. But also, say it's C infinity and smooth, or Schwartz. Those are all dense inside of LP when P is finite and bigger than or equal to 1. So monotone convergence says, if you give me some LP function, and I can approximate it, this density says, if you give me an LP function, I can approximate it by a nice function. For our cases, that'll be just smooth and compactly supported. So say C infinity, compact support. And the monotone convergence says that you can follow the sequence of smooth, compactly supported functions that approximate your function in LP And you just take some increasing sequence to it. And so if you show that the maximal function on all compactly supported smooth compactly supported functions satisfies the right bound, then by monotone convergence, it satisfies the right bound for that limit function that we're approximating. Okay. The second step is a bit harder to see. It turns out that the characteristic function of a ball, so one of, say, B, a ball, is a smooth enough function. While it is has a whole set of discontinuities on the sphere, on the boundary of the ball, it is obviously continuous inside the ball, where it's always 1, and is continuous outside the ball, where it's always 0. And it's C infinity even inside those regimes, but it's at the boundary where it's not. Still, that boundary is measured 0. And it turns out that these averages are smooth. That's actually just a higher dimensional phrasing of what I said a few moments ago, where, if I start with a continuous function, I look at an average, I end up with a continuously differentiable function. It's continuous. This was referring to f, or the argument of f, but it's also continuous in R if I start with a nice function. So since this is continuous as a function of R, we can use monotone convergence to only consider balls whose radii are rational numbers, positive rational numbers, because I can approximate any real radius by a rational radius that is arbitrarily close, and the difference between those two balls is tiny, infinitesimal. Now, another monotone convergence argument allows you to actually truncate. So that gave us a countable parameter, a countable family of radii. Monotone convergence again says you can actually get any finite set of positive rationals. But the catch is, I cannot let these bounds depend on the size of R. And in previous arguments, I couldn't let the bound depend on the function except in the prescribed way, right? It's LP norm. Also, since our maximal function is defined as the supremum, well, actually it's written right here. So originally our maximal function was this being all positive R, and now it's R in some finite set that we don't really have control of over at all. It's just an arbitrary finite set of positive rational numbers. But we see that if we just take this and we go that this is less than or equal to moving the absolute value in, it's less than or equal to the sup over R and R of the absolute value of f, and the averages of the absolute value of f. So we just need to show this when our function is non-negative. And that's because the LP norm of f is equal to the LP norm of the absolute value of f, right? In defining the LP norm, I took the absolute value to the pth power and to the 1 over p. So there's nothing lost by just assuming f to be non-negative. Great, that brings us to the weak 1-1 bound. Now I'm going to make the constant precise that we wanted to use, that we need to have in our bound. So this constant, before I was saying it's CD, I was writing RD, now I'm writing RN, and the constant is going to be 3 to the n. Before, I didn't actually say, I need to include the boundedness on L infinity. That was supposed to happen right here. We have that. So A R f of x is So if f is less than m everywhere, oh, m's a bad choice. Let's pick an actual number. F is less than 10 everywhere, then the average, any average, is less than or equal to 10 everywhere, which implies that the maximal function is less than or equal to 10 everywhere. Okay, or in other words, the maximal function in L infinity is bounded by the L infinity norm of our original function. There's no loss of a constant here. It's a constant 1. Now, the weak type 1,1 bound is going to have the constant of 3 to the n. So it grows with the dimension, whereas the other one did not at all. It was just a 1, and it just, you started with your function bounded by 10, the maximal function is bounded by 10 everywhere as well. Very simple, straightforward. This now says that, oh, we don't have a function that's bounded, or at least we can't say it's bounded by 10, but we can control these level sets like this. Great. Are there any questions about what we're trying to prove now? All right, let's see what I've written before. Not much. Yeah, I'll give another moment for questions to take a sip. Okay. This is a absolutely gorgeous proof. It's one of the, I think it's one of the theorems and proofs that made me, want to do mathematics, because you start with something that I still haven't justified as being a good thing to do, which is study this maximal function. But taking that for granted momentarily, we have this bound that, at least when you first come across it, there's absolutely no reason to suspect to be true. And the proof turns out to be a pretty nice sort of geometric combinatorial argument. Okay, let's get into how to do this. At this stage, we have a supremum, our maximal function, just to recall, is a supremum over some finite set R that we don't have control of. It's just positive rational numbers, a finite number of them. We don't know which ones. And well, actually, I moved the absolute value inside, right? Great, so my function f is non-negative. And we want to prove this bound. So let's try and do so naively. We know that we said f is an L1, and we said f is also smooth, compactly supported. Let's call that support K. So it's contained in a compact set K. Great. So outside of 2K, call support of K, not quite the support. There exists a ball B. K, sorry, there exists a ball K. Closed and centered at the origin. That contains the support of F. Right. So outside of 2K, right, it's the same picture I was describing a few minutes ago. Outside of 2K, my function 0 everywhere. So the average, the maximal function is going to take an average that actually contains K, right? And when it does, we know that, well, we know roughly how big the maximal function is. the maximal function is like up to some constants I'm not making too precise right now. It's about x to the minus n inside of Rn. And if you choose x large enough now, I guess the absolute value, then this side is is arbitrarily small, right? In particular, it'll be smaller than alpha. What that tells me is that this set right here, the super level set, is contained in a compact set itself. Let's call that K prime. You can choose K prime sufficiently small, or such that it's also contained inside the maximal function greater than, let's say, C alpha, for C smaller than 1 but close to 1, maybe 0.99, right? There's a little bit of a gap here, basically. Let's say it's at least a half. Okay. So let's write out what this means. I can find for each point x in K prime, there exists some ball, say B of R, well, so radius really. There exists some R in R, such that the average of my function at that point is greater than alpha. Just by oh, C alpha, sorry. Okay. Great. And if I was actually inside of K, then I could replace that C with a 1. All right. Not K, sorry. No, this is definitely K prime. Great. I plugged in a definition. What does that do? Well, let's try and just write out what that is explicitly. So the average is 1 over the ball of radius r, integral over b of r, f of x minus y dy, right? And I'm saying this is greater than c times alpha. That's equivalent to, of course, just moving this side over, the volume over, the integral of f of x minus y dy is greater than c alpha times the volume of br. And now what is K prime? It's a compact set, so there's some covering of K prime by a bunch of balls. A finite cover of balls. Let's say set BI. I is from 1 to n. And so you might just be like, oh, okay, at this stage, well, I just do the integral over the sum over the balls of f of x minus y dy is greater than alpha c sum over the balls bi, right? The I is indexing the sequence of balls now, not indexing the radius of the ball. But this thing is not equal to the union of all the BIs. Which would contain K, or contain K prime, and hence K, and therefore give us the L1 norm of the function. Instead, it's something a bit bigger. And similarly, there's a bit of overlap here. But this argument is actually too far off. This idea of just writing down the balls, blindly applying things, isn't too far off. The cleverness comes in the Vitali covering lemma, which tells us that if you gave me any finite collection of balls, the ones coming from K prime, right, the B1 through Bn, there's a disjoint sub-collection of balls, B1 through Bm, such that this containment is true. So what do I mean by 3bi? If I say I have some constant kappa times a ball B, that is the ball whose center is the same center as B, but the radius is now kappa times the radius of B, right? So if I have a ball here in space, that's B, then 2B is the one with same center, but twice the width. And the Vitali covering lemma says that, okay, 2 doesn't work here maybe, but 3 does. I just take the balls and I triple their radius, triple their width. And I can find some sub collection when I do so that is disjoint. How do we prove this? Well, it's just a greedy algorithm, which is a very simple but effective algorithm in this context. What do? You give me a whole bunch of balls. So my set K, let's draw it. My K prime is some set. Okay, and my K was maybe some other set inside. Oops. K, we said, had a bunch of balls covering it. And now in our picture, all we've done, or what we've done so far is we've discarded any of this black body and this yellow sub body of it. And we're just left with this collection of balls, and their overlapping collection of balls. What the greedy algorithm tells us to do is identify the biggest ball. That'll be this one. And call that B1. So these blue balls are my B1 up to Bn. And now my sub collection, which I'm re-indexing, is going to start with B1, the biggest ball. And out of my blue collection, I'm going to throw out all the balls in 3 times the radius of that biggest one. That gives me some sub collection to worry about. And now, sorry, that's all the balls contained inside of it. But I have some balls that only partially overlap with it, namely these green ones. And what do? My B2 now is I just identify what is the biggest one of those. And I throw out any ball that lies in 3 times it. Then I go to the next one and identify the next biggest ball, put it in my collection, throw out any that overlap with it with 3 times it, and so on. This is clearly an algorithm that terminates because I only started with finitely many balls to begin with. So after n steps, it's dead. If they're all very far apart, I started with n balls that are far apart from each other. And it's possibly ends much sooner. But we also have this property that we get this containment because of the greediness of our algorithm. We threw out anything that was properly contained inside of it when we refined our collection. So that's pretty cool. Now, once we have that in hand, it's pretty easy to complete the proof of the week 1 bound. I'm going back to our formulation from before, right? Where I multiplied by C alpha. I had oops. I had A or F of X was greater than C alpha, was equivalent to the integral over B of R, F of X minus Y dy is greater than C alpha BR. These BRs were covering our compact set K prime, which contains this. So I just take those balls. That should be, and I refine that subcollection. This B star is 3B. And what is the volume of a ball compared to 3 times the ball? It was just 3 to the n times the volume of the original ball. And now when I sum these up, I use this inequality right here. I plug it in. And that, since the BJs are disjoint, I actually get to include that that's at most the L1 norm. This is at most this. And now just by expanding C towards 1, so that you shrink K prime to actually be the right compact set, you get the right bound. Right, this C becomes a 1, and we obtain what we want. That's alpha MF greater than alpha. It's less than or equal to 3 to the n F and L1. And you just move the alpha over to get the statement that we started with. Great. Are there any questions there? I know for most of this audience that I'm talking to right at the moment, they are familiar with it. But if anyone has not seen this, excessively, any question would be a great question right now. Okay, I will end the recording there for today. And we'll resume with how to use this and interpolation to get the LP inequalities, and then some applications of the maximal function. Why is actually something we should care about.